Deep inside a massive mineral processing plant, everything begins with a single rock. Heavy trucks arrive one after another, their beds loaded with raw ilmenite and rutile ore, dark mineral rock pulled straight from the earth. At the weighing station, every batch is precisely logged. Weight, chemical composition, purity percentage, nothing moves forward without laboratory confirmation. The raw ore enters massive jaw crushers. Powerful machines break it down into a uniform grade, ready for the next stage. Magnetic separators pull iron impurities away with incredible precision, leaving behind a concentrate rich in titanium. Inside chlorination reactors, at temperatures exceeding 800 degrees Celsius, the ore combines with petroleum coke and chlorine gas. The result? A gas called titanium tetrachloride, the raw material that will soon become metal. This gas is cooled and liquefied in distillation towers, purified and sent into the Kroll reduction vessels. Inside these reactors, in a sealed argon atmosphere, molten magnesium reacts with titanium tetrachloride. At 850 degrees Celsius, something extraordinary happens. Metallic titanium is born, a porous, gray, sponge-like mass known as titanium sponge. A journey that began with a simple rock has now reached the material that will conquer the sky.
Raw, porous titanium sponge is ready for its transformation. In the crushing hall, large sponge masses are broken down under powerful industrial crushers. Silver-gray particles fall onto vibrating screens, each size fraction directed to its exact destination. In the alloy preparation room, crushed sponge is precisely weighed and blended with alloying elements, aluminum, vanadium, and others. The ratios are exact. There is no room for error. The alloyed mixture is compacted under massive hydraulic presses into dense cylindrical electrodes, solid metal rods ready for melting. Inside vacuum arc remelting furnaces, tens of thousands of amps pass through the electrode. The electric arc burns with blinding intensity. Metal melts, drips, and solidifies into a solid ingot inside a water-cooled copper crucible. This process repeats 3 times, eliminating every trace of impurity from the metal structure. The final ingot is a massive silver cylinder, weighing up to 10 tons. After cooling, the ingots are inspected. Ultrasonic scanners probe deep into the metal. Every crack, every void, every inclusion must be found before moving forward. Then, in reheating furnaces, the ingots reach forging temperature and are shaped under enormous presses. The hot gray metal is transformed into slabs and billets, and hot rolling stretches it into long, thin plates, silver, gleaming, ready for the next stage. Rolled titanium must now rest. In continuous annealing furnaces, the plates move slowly through heated tunnels. Temperature is precise. Time is precise. The metal's grain structure forms here, the very structure that determines its final strength. In acid pickling baths, the dark oxide layer is stripped from the surface. The titanium plate emerges bright and silver. Precision grinding machines flatten the surface to a mirror finish. Laser and water jet cutting stations carve exact shapes from the plate. No material is wasted. Every cut follows an optimized nesting pattern. In the atomization unit, molten titanium becomes a stream of tiny droplets, micron-sized silver spheres that solidify in an argon atmosphere. This powder is the feedstock for metal 3D printing. In CNC machining halls, complex aerospace components are carved from titanium billets with micron-level precision. And in 3D printing suites, powerful lasers build components layer by layer, geometries impossible by any other method. In the medical division, hip, spine, and dental implants are produced with tolerances the human eye cannot even perceive. And in automotive forging presses, connecting rods and valves for high-performance supercars are shaped under precision dies, lighter than steel, stronger than imagined.
Making a component isn't enough.
it must be proven correct. In heat treatment furnaces, titanium parts soak at controlled temperatures for precise durations. This process pushes the metal's mechanical properties to their limit: strength, hardness, fatigue resistance. In PVD coating chambers, titanium nitride coating is applied. A violet blue plasma glows inside the chamber, and parts emerge coated in a golden layer, harder than the base metal, resistant to wear. Phased array ultrasonic inspection scans the interior of every part. Volumetric maps of the metal's inside appear on screen. No internal flaw stays hidden. Industrial CT scanners build photographic quality 3D images of a component's internal structure, technology once reserved for medicine, now serving the aerospace industry. Coordinate measuring machines touch every dimension with a tiny ruby probe. Color deviation maps appear on screen. Green means approved, red means review again. Medical implants reach a mirror-smooth finish in electropolishing baths, leaving no surface for bacteria to hide. And in medical titanium anodizing, tiny bone screws take on beautiful spectral colors, not for beauty, but for size identification. Finally, final inspection confirms everything. Green tag for shipment.
A finished part must be complete, not just in shape, but in cleanliness. In automated cleaning systems, titanium parts pass through degreasing, rinsing, and drying stages. A technician checks a wipe sample under UV light. No hydrocarbon contamination remains. Full traceability activates. Every part carries a laser-etched serial number, linking it to every production step, every operator, every batch of raw material. If a question ever arises, the answer already exists in the system. Medical implants are sealed in sterile pouches, inside clean rooms rated ISO Class 7. Every heat seal is precise. Vision cameras confirm every barcode. Aerospace components are placed in custom wooden crates with precisely cut foam, wrapped in VCI film, ready for their journey to aircraft manufacturers. Supercar components are grouped in packaging labeled with vehicle model codes and production sequence numbers. Just-in-time delivery. Every minute the line waits costs money. In the massive warehouse, automated cranes move pallets with speed and precision. Every product knows where it is and where it needs to go. And from the logistics office, final coordination happens. Aerospace, medical, and automotive orders managed simultaneously, because none of them can afford to wait.
Titanium's journey is nearing its end, but not before reaching its true purpose. At an aerospace receiving dock, titanium components are carefully unpacked. Every dimension is measured. Every material certificate is verified. Only after approval does the part enter the production line. In an operating theater, a surgeon holds a component that has passed through thousands of processing steps. A hip implant, about to change a person's life. Its surface is mirror smooth. Its dimensions are perfect. This moment was the true purpose of all that precision. In a jet engine assembly hall, titanium compressor blades lock into place one by one. Every bolt is torqued to exact specification. This engine will run for thousands of hours at 35,000 feet. On a supercar assembly line, titanium connecting rods settle into the engine block. A titanium exhaust is installed. This car, destined to set records on the track, is being born today. At 35,000 feet, an aircraft cruises through the clearest blue sky. Hundreds of titanium components work within it, silent, reliable, tireless. And in an aerial view of the entire industrial complex, everything comes together in a single frame, from raw ore trucks to final product shipments. This is the titanium industry. Billions of dollars, thousands of people, one material. A material that makes the sky, the human body, and speed itself possible.